My name is Florian and I'm going to present our recent work where we propose to leverage geometry for shape estimation from a single RGB image. The input to our model is a single RGB image, and the output of our system are aligned 3D shapes for the objects observed in the image. Existing work either directly predicts object shapes, which produce unrealistic results, or retrieves objects, but directly predicts poses, which is inaccurate and limited to objects available in the database. In contrast, we propose to retrieve CAD models from a database, which are then adapted and aligned based on geometric considerations. This is our method overview. The input to our model is an RGB image. We also have a database of CAD models, which we render from different orientations. The RGB image is fed into a segmentation network to produce segmentation masks of the objects observed in the image. Each of the masked objects is the input to an encoding network. This encoding network is trained in a contrastive learning framework. For a given masked RGB image, positive examples corresponding to the same CAD model in a similar orientation and negative examples corresponding to different rendered CAD models are found. Their encodings are used in a triplet loss, which ensures that masked RGB images are embedded close to the renders of objects present in the image. At test time, for a given RGB image, nearest neighbor CAD models are retrieved. These then serve as the input to a matching network, which matches key points between rendered and real images. For the rendered image, ground truth 3D coordinates are known, such that matches establish 2D to 3D correspondences, which can then be used to adapt and orient a retrieved CAD model to make it more similar to the target. The shape adaptation we propose is a plane stretching formulation, where objects are stretched along a plane. Depending on the position and orientation of the plane that is chosen, different objects can be generated. Mathematically, we obtain stretched object vertices by adding an offset to the vertices x parallel to the plane normal n. We optimize over the magnitude of the stretch tau. We show results here where we optimize over just the pose of the objects. Keypoint matches allow us to make very accurate shape and pose estimates. We train and test our system on the Pix3D dataset. We compare quantitatively against pixel to mesh and mesh RCNN, which are direct shape prediction methods. We also compare against mask to CAD and patch to CAD, which similar to us retrieve CAD models from a database. We outperform all competitors on different data splits on all metrics by a large margin. Further, we demonstrate good adaptation results when no access to correct models is given at test time, and the retrieved CAD models have to be adapted. Thank you for your attention.